Welcome to Lecture 7. In this lecture, we will be discussing air pressure and winds. We've already discussed air pressure in the first lecture, right? Talking about how it's basically the force or weight of air molecules per unit area. And we will be discussing it in more detail here. How it's measured, how it changes as you go up in height or you go horizontally on Earth's surface. And we'll be discussing winds, because air pressure and winds are somewhat related. In fact, they're very related in the sense that differences in air pressure drive winds. At the surface, horizontal differences in pressure, differences in air pressure with respect to a horizontal direction will give horizontal winds. Turns out that pressure rapidly decreases with height in the atmosphere, and there's a strong pressure gradient directed upward, but because of the force of gravity, air doesn't rush off into space. So we'll be talking about wind direction and speed. How are they measured? So to start, here's a review of some of the important concepts we covered back in Lecture 1 about air pressure, as well as some questions we'd like to be able to answer. Air pressure is the weight of air per unit area. Air is surprisingly heavy. Air is made up of molecules, and those individual molecules have weight. And there's a lot of molecules above Earth's surface. And air pressure always decreases with height. That's because as one travels upward in the atmosphere, there are fewer molecules of air above. Okay? I went to South Lake Tahoe area last weekend, mid-October, and did a hike of Mount Talac, which gets to near 10,000 feet. And near the top, there's about 30% less pressure than at sea level in San Jose. So you definitely notice it. The pressure is less, but also the air density is less. Okay, and so at the top, there's a lot less pressure on you, weighing down on you, because you're above so many molecules. We'd like to answer the question, though, what causes air pressure to change in the horizontal direction? We know how it changes in the vertical direction, but what drives horizontal winds? Okay, north winds, south winds, east winds, west winds, or winds with components in those various directions, are horizontal differences in pressure. And it turns out, the greater the difference in air pressure over a horizontal distance, the stronger the wind. So we'll be talking about the different forces that cause air to move. And why does air pressure change at the surface? If you've watched the news, weather reports, or the Weather Channel, you've probably heard about areas of low pressure, areas of high pressure. Areas of low pressure at the surface are generally associated with rising air and active weather, such as clouds and rain, whereas high pressure at the surface is generally associated with sinking air and therefore dry conditions. But why does air pressure change at the surface? Okay, why isn't it always the same? We'll talk about that. So, we're going to start understanding how a variation in temperature alone can drive winds. Okay, a difference in temperature between two places that are separated by horizontal distance can drive winds. So, to help us understand this concept, let's talk about an air column from a simplified perspective. You know, models are basically representations of real things in the world. Like, for example, a model car, it's a representation of a car, but it's simplified, right? Models usually make simplifications because they're designed to replicate something in the real world, but not to the full detail. Okay, so you'll see the model car from far looks real, and then you zoom in on it, right? You get close to the old Ford Mustang convertible model car, or VW Bug, or kids today, maybe they play with Toyota Prius and Tesla model cars. You see it's simplified, right? It's not as fine in detail. So there's some assumptions made. Let's assume for this air column, there's constant air density from the bottom to the top. Okay, started from the bottom, now we up here. Assume constant air density. This isn't real in the atmosphere. I mean, you know how air density is usually highest near the surface? The air molecules are crowded close together at the surface, and density decreases as you go higher up, right? Air becomes thinner as you go higher up. That's because the force of gravity pulls down molecules close to the surface. So this isn't quite true. And you might be asking, well, why are we making these assumptions that aren't true? It's because it'll help us understand an important concept. We're using a model to try to help us understand concept, but make it easier to understand by not making it simpler. Okay, and the molecule has constant width. The column has constant width, and this could be true. I mean, you can think of an air pressure, right? Remember, average air pressure at sea level is about 14.6 pounds per square inch. So you can, think of air columns, right, which have certain areas and they go vertically upward in the atmosphere. An air column, 1 square inch in area at the surface at sea level would weigh 14.6 pounds if it extended throughout the atmosphere. And let's assume that air can't move in or out of the column initially. In the real world, air does tend to move, right? Wind, and we did talk about this, a similar concept when we talked about adiabatic processes. Those air parcels are independent, right? They can't exchange heat or moisture with the surroundings. Let's assume initially air can't go in or come out. So we have this air column with the same density throughout, and it has these molecules in it, and the molecules can't go in. New molecules can't come in, and these molecules can't go out, and it's a certain constant width. Okay? So it turns out it can expand upward or downward, but let's assume it doesn't expand horizontally. Now, continuing on with this theme, let's assume you have 2 air columns, each with identical mass, right? So the same number of molecules in each, with the same surface pressure over 2 cities. Here's city 1, right? Maybe this is LA, and here's city 2. Maybe this is San Francisco. Okay, maybe this is Seattle and Portland, right? So initially, let's assume they have the same temperature and the same amount of molecules in each column, and so you see they're the same thickness. Now, let's assume that City 1 experiences a cooling, perhaps, or City 1 gets colder. So now the molecules crowd closer together. Remember how in colder air, the molecules do not move as fast, right? Colder air, lower temperature molecules have less average kinetic energy. Now the molecules are not moving as fast, so they crowd closer together. Remember, we have a constant width, basically constant area. So we're not going to be able to expand the column horizontally, but we can expand it up or down. And so the molecules go close together, and so it shrinks vertically, right? See that? It shrinks. Now, City 2, which, remember, initially City 1 and City 2 have the same pressure, therefore the same number of molecules in those fixed width columns, warms. It warms up, therefore the molecules now have greater average speeds, and the molecules expand vertically. And so the air column, as you see, rises vertically. It expands vertically. Again, because air is not allowed to move in or out of the columns, the pressure remains the same. Even though they're different sizes, there's still the same number of molecules in each, and therefore the same pressure. But Even though the pressure is the same at the surface, it's not the same at a certain height. Let's assume you go up to a particular height here. This height right here, see, in this part of the figure. If you're at this level in the warm air column above city 2, look at how many molecules you still have above you in that warmer air. Whereas if you're at the same elevation above the surface, same height in the air column 1 over the city 1, the cold air column, there's far fewer molecules above you because it's colder, and so in colder air, the pressure decreases more rapidly with height than in warmer air, the air pressure decreases less rapidly with height. So that develops high pressure aloft. Aloft just means in the upper atmosphere, or above the surface, really. And low pressure aloft associated with cold air. This is an important concept. Because in the cold air column, you're going to pass more molecules with height, your pressure decreases more rapidly. At the same elevation, the air pressure will be lower than in the cold air column than in the warm air column. Now that pressure difference creates a force that wants to move air from high to low pressure. Air always wants to move from high to low pressure. It never wants to move from low to high pressure. And now, remember how we said that air can't move in or out of the column, right? Maybe they have some invisible elastic around them. Now let's assume that they can. They're not closed off. Let's assume now that air can move in or out of the columns. You know what would happen is at this height, because of a higher pressure here for this air column over city 2 and a lower pressure here in this air column over city 1, air would move from high to low pressure. And therefore, you get wind. You get horizontal wind moving from city 2 to city 1. So then think about it. You're taking air out of the column above city 2. You're adding air into the column of city 1. Above city 1. What happens to the pressure at the surface for city 2? It goes down because you're removing air, right? Surface pressure is the weight of air per unit area. The more molecules above the area, the more pressure. So you're removing molecules from this column. Pressure falls, it drops, it lowers. You're adding molecules above the city 1, so its pressure rises. Okay. The horizontal difference in temperature creates a horizontal difference in pressure. This establishes a force called the pressure gradient force, which causes air to move from high to low pressure. And it's very interesting because remember how you had high pressure aloft for the warm air column and low pressure aloft for the cold air column? Well, at the surface, because of that horizontal movement from the warmer air column to the cold air column, now the pressure at the surface for the cold air column rises. And that leads to high pressure here at the surface, whereas the surface pressure at the city 2 decreases, and so you have lower pressure. Okay, and what you see is that a complete circulation of air is formed solely by differences in temperature. Okay, so differences in temperature drive differences in pressure, which drive winds. The pressure gradient force is caused by horizontal differences in pressure, and it is responsible for the formation of horizontal wind. That's why the wind blows. What causes air to move initially and horizontally at the surface? Differences in horizontal pressure. Now, once the air starts moving, it's subject to other forces, which we'll be discussing, like friction slows it down, Coriolis force due to the rotation of the Earth. We'll talk about them in more detail. But the initial driver of wind, horizontal wind, is the pressure gradient force. Now, here is a figure showing extreme sea level pressure values. Basically the range of sea level pressure across the surface. You know, standard sea level pressure has a value of, you may recall from lecture 1, 1013.25 millibars. And because 1 millibar equals 1 hectopascal, 1013.25 millibars is equivalent to 1013.25 hectopascals. And that's also equal to 29.92 inches of mercury. And here's your standard sea level pressure, 1013.25 millibars. A deep low pressure system, such as for a really strong storm, might have a sea level pressure of 980 millibars. Strong high pressure systems can have values of 1040 millibars or even higher. Highest recorded sea level pressure in the continental United States was in Miles City, Montana. December 1983, the mercury column in the barometer reached 1,064 millibars. Okay, very high. Definitely you would notice that. Your body would detect that. It's very much higher than normal pressure. Kind of interesting, it says in the continental United States, excluding Alaska, because I thought Alaska wasn't part of the continental United States. That might be kind of redundant. Anyway, the highest recorded sea level pressure for the world occurred in Mongolia not that long ago, actually less than 12 years ago. 1,092 millibars. That's just incredible. That is close to 10% higher than average. Okay, about 8% higher. May not sound like a lot, but trust me, your body would definitely notice that. During landfall, Hurricane Katrina had a sea level pressure of 920 millibars. The center of the hurricane has the quote-unquote minimum pressure, 920 millibars. It had been lower, but thankfully, Hurricane Katrina did weaken slightly before making landfall over New Orleans. Still did a lot of damage, right? Still flooded the city. The storm surge flooded much of the Mississippi coast. And it's taken years for the city to recover for New Orleans, but it could have been even worse. Thankfully, it did weaken as it entered some cooler water. But it was still a very strong Category 3 regardless. But it could have been a Category 5. Hurricane Wilma has the record as lowest pressure, sea level pressure for an Atlantic hurricane. Okay, in October 2005, actually only a couple months after Katrina, it had an incredibly low sea level pressure of 882 millibars. And it turns out the lower the pressure at the center of a hurricane, basically the stronger the winds, okay? Because the greater the pressure difference with respect to the horizontal direction, which causes winds to blow. Lowest recorded sea level pressure ever on Earth was actually at the center of Typhoon Tip in October of 1979, 870 millibars. Now, as low as that seems, actually, on average, Denver, Colorado, okay, the mile-high city, called that because it's 5,280 feet above sea level, actually has its average pressure is less than that. It's about 850 millibars, okay? South Lake Tahoe's average actual pressure is closer to 830, 820 millibars. But it turns out, when you want to talk about winds, differences in horizontal pressure causing winds, you need to talk about sea level pressure, because pressure changes much more rapidly in the vertical direction than the horizontal direction. And if you only look at surface pressure, actual pressures on Earth, they can deceive you, and they can't. That won't tell you about the horizontal winds, because the differences in elevation will override the differences in horizontal pressure that cause winds. By the way, Hurricane Patricia made landfall in western Mexico late last year, and it had a minimum pressure of 879 millibars, which actually was the new record for lowest sea level pressure in the Western Hemisphere. That distinction had been held by Hurricane Wilma. It still has the lowest sea level pressure ever in the Atlantic Basin, but the new Western Hemisphere, right, east of the international date line, west of the prime meridian, lowest sea level pressure occurred during Patricia. Incredible maximum sustained winds of 200 miles per hour. That's a strong tornado speed, and that's extending out for miles from the center. Okay, incredible. You know, I've seen 150, 160, 170, 175 mile per hour sustained winds, but I had never seen a hurricane with sustained winds this high. There were gusts of 230, 240 miles per hour. Okay. Now, granted, that's only near the center. The winds decrease as you go outward, but still, just incredibly strong hurricane. Thankfully, it made landfall over a lot of mountains, which helped weaken it. And also, there was a lot of warning before, preparations, so the damage was not nearly as high as it could have been, thankfully. Okay, people were prepared, and thankfully the topography helped weaken it and take down those winds after it made landfall before it started reaching more densely populated areas. Okay. Air above a region of surface high pressure is more dense than air above a region of surface low pressure at the same temperature. Comes back to what we were talking about earlier. If you have two molecules, columns of air with the same temperature, and so the molecules are moving at the same speed, then if you have more molecules, basically that means a higher pressure. If you have less molecules, that means a lower pressure. What meteorological instrument measures air pressure? It's the barometer. The barometer measures atmospheric pressure. The mercury barometer uses mercury in a column of a tube to measure pressure. It consists of a long glass tube here, kind of like a test tube in chemistry, except longer, open at one end and closed at the other. The open end is placed in a dish of mercury. And the height of the mercury in the column of the tube is a measure of the pressure. If the pressure increases on this dish, the mercury expands. If the pressure decreases on this dish, okay, less air weighing down on it per area of dish, the mercury contracts. Okay, on average, it would have a height of 29.92 inches, which is about 2.5 feet. Okay. The mercury barometer was invented by Evangelista Torricelli, a student of Galileo's, in 1643. So it's more than 400. It's more than 350 years old. Okay. It's about 373. It's 373 years old. Now, just so you know, there can be errors in the measurements. See, all mercury barometers are corrected as if they were read at the same temperature. Because remember, temperature would affect the height of the mercury too. Remember how thermometers work, right? So the barometers are corrected to be read at the same temperature to take out differences in height and therefore errors in pressure because of temperature differences. Now, the Earth is not a perfect sphere. It bulges slightly at the equator, it's squished slightly at the poles, so the force of gravity is not constant over Earth. Small gravity differences can influence the height of the mercury in the column, and also each barometer has its own instrument error caused by surface tension of the mercury against the glass tube. Nonetheless, mercury barometers are still fairly, in fact, very accurate. Even though there are some uncertainties and errors, they're still pretty accurate. Okay. Now, there's another type of barometer that you may know about that's used to measure atmospheric pressure. It's called the aneroid barometer. And it's actually the most common type of home barometer. It does not contain any fluid. This one looks kind of like an old alarm clock, but there's also the aneroid that look more like a wall clock, where you just see the numbers and then the dial. And the numbers might be inches of mercury. For this one, the numbers are in millibars. So it doesn't have fluid. Inside of the aneroid barometer's instrument, inside of this instrument is a small, flexible metal box called an aneroid cell. Okay. Before the cell is sealed tightly, some air is removed so that small changes in external pressure, right, will cause the cell to expand or contract. The size of the cell is calibrated to represent different pressures, and any change in size, expansion if pressure increases, contraction if pressure decreases, is amplified by levers and transmitted to an indicating arm or hand, like on a clock, which points to the current pressure. So if it expands, the aneroid cell expands, the dial, the arm, moves to the right. If it contracts, it moves to the left. Notice this aneroid barometer has descriptive weather-related words printed above specific pressure values. The descriptions indicate the most likely weather conditions when the needle is pointing to that particular pressure. So, for example, if the sea level pressure is 980 millibars, that indicates generally stormy conditions. It's very likely that there'll be heavy rain with that low of a pressure. 990 to 1000 millibars sea level pressure, still rain is generally associated with rain or perhaps showers. 1010 millibars is kind of a point where you look for changes, because if the pressure decreases to below that, that's a signal of a storm coming. But if the pressure is increasing above it, that's a signal of clearing conditions. Fair weather would be associated with pressures in the 1020 to 1030 millibar range. And once the pressure gets to near 1040 millibars, it's generally very dry. Generally, the higher the reading, the more likely clear weather will occur, and the lower the reading, the better the chances for inclement weather. The situation occurs because high pressure areas at the surface are associated with sinking air and usually fair weather, whereas low pressure areas at the surface are associated with rising air and typically cloudy, wet weather. Okay, now we need to discuss the difference between sea level pressure and station pressure. The barometer reading at a particular location, regardless of elevation, is called station pressure. This is the pressure that's been corrected for temperature, gravity, and instrument error. Since pressure varies with altitude, right, with elevation, the pressures at stations of different elevations need to be corrected in order to compare them, especially if you want to look for differences in horizontal pressure, which drive horizontal winds. The adjusted pressure to sea level is called sea level pressure. Pressure decreases much more rapidly in the vertical direction than the horizontal direction. And again, Denver's average actual pressure is about 850 millibars, lower than any hurricane or typhoon sea level pressure ever recorded. Denver's only a mile high, so you only have to go a mile up for actual air pressure to decrease by about 10%, 15%, right? Roughly 1,000 millibars to 850 millibars. Now, here's a figure from the book with different parts illustrating how pressure decreases with height and how it's corrected. Here are 4 cities with different elevations above sea level and therefore different station pressures. Here's the sea, right? And here's city A at 600 meters, about 2,000 feet above sea level, with a pressure of an actual station pressure of 950 millibars. City B is at the elevation half of A, so it's more like 1,000 feet above sea level. Pressure there, actual recorded pressure, station pressure is 979 millibars. City C is at an elevation of 1,100 meters, which is about 4,000 feet above sea level, close to that. And it has a pressure of 894 millibars. That's the station pressure. Finally, city D here is actually on the beach, basically, on the coast. It's at sea level, so its station pressure, which is 1,000 millibars, is equivalent to its sea level pressure. Okay. Now, in the middle diagram, B, it shows how the sea level pressures are plotted after they've been corrected. Near the surface, atmospheric pressure decreases on average by about 10 millibars for every 100 meter or 330 feet rise in elevation. So here's the rule. For every 100 meters above sea level, add 10 millibars. How high is city A? 600 meters. 100 meters means a 10 millibar change in pressure. A 100 meter increase in height would lead to a 10 millibar decrease in pressure. So because city A is at 600 meters above sea level, you have to add 60, right? 600 divided by 100, 60 millibars to find what its pressure would actually be if it was at sea level. 952 plus 60, 1012 millibars. How about city B? Well, 300 meters. To go down 300 meters, you'd have to add 30 millibars to find the actual pressure at sea level, not the station pressure. So you have 30 millibars, you get 1,009 millibars. You continue correcting. And when you do this, then you'll actually see sea level pressure, and now you'll be able to start looking for the wind direction and speed. And we'll talk more about how to do this, how to use sea level pressure on a weather map to find wind direction and speed. Okay. So then what's done is isobars are drawn on the chart, shown by the dark lines, at intervals of 4 millibars. Okay? What do you think an isobar is? What's iso? Basically equal. Bars, okay, are a unit of pressure. Remember millibar? That's basically a thousandth of a bar. Okay, so basically isobars are lines of equal or constant pressure. And they're drawn on weather maps at intervals of 4 millibars, unless the map is really zoomed in, and then you might draw it even smaller, lower, higher resolution, but less of an interval. Generally 4 millibars they're drawn at, with 1,000 as a base contour. 1,000 millibars, 1,004, 1,008, 1,012 millibars. So here are dots showing not the actual station pressure, but the sea level pressure of different locations. And then isobars are drawn. And the way to do that is basically connect the dots. Wherever you see 1,012 millibars, where you know 1,012 goes through there. And then what you do is linearly interpolate. If 1,014 millibar sea level pressure is found at this location, and this location has a 1,010 millibar sea level pressure, well, 1,012 has to go halfway between. Okay, so that's how it's done. Then isobars show you differences in horizontal sea level pressure. So notice as you go this direction toward the what? Well, this is north, right? So this would be toward the east. Pressure decreases. Okay. As you go toward the east, pressure is decreasing. Sea level pressure is. Okay. We'll talk about the closer the isobars are together, the stronger the winds blow. So, here are some important terms to understand when you analyze surface and upper air charts. Surface charts show isobars, which are lines of constant pressure. Okay? Whereas upper air charts show contour lines, not isobars, but contour lines, which are lines that connect points of equal elevation above sea level. So a surface weather map will generally show sea level pressures, and so it'll basically assume sea level elevation and show the pressures. So it plots pressures. But an upper air weather map, which you could use a weather balloon to help you draw, use weather balloon observations to help you draw, is actually taken at a fixed pressure level. For example, 500 millibar map shows heights, contour lines, heights at 500 millibars, okay? Lines of low height correspond to regions of low pressure, whereas lines of high height on an upper level weather map or upper air chart show regions of high pressure. And sometimes on these upper air maps, as well as on some surface maps, lines of constant temperature are drawn, which are known as isotherms. Illustrating here how higher heights, higher contour line values on an upper air map are showing higher pressure. Here's a 500 millibar surface. It's not flat because this is the surface. This is how high you'd have to go up to drop from 1,013.25 millibars pressure at sea level to 500 millibars, basically cutting your pressure in half. In warmer air, molecules move faster and they expand more, so you have to go higher up, right, to drop to 500 millibars. Whereas in colder air, the molecules are closer together, and so air pressure decreases more rapidly and you don't have to go up as high, okay? So if you're at a constant height, let's assume you're at a constant height here, shown by the, see how this is basically a rectangular solid with this slab that varies in height in kind of going through it. Assume you're at this average height here. In the cold air, your pressure would be less than 500 millibars, right? You're above the 500 millibar surface. But in the warm air, at the same height elevation, you're at higher pressure. More than 500 millibars, still above you. So basically, warm air aloft is associated with high pressure and high contour values. Lower contour values indicate lower pressure and cooler air. South, north. As one travels north in the northern hemisphere, on average, temperatures drop as you increase latitude, and so the height contour values go down. But as you go further south in the northern hemisphere toward the equator, it generally warms up, height contour values increase. And here's another figure showing a surface of constant pressure, as well as how the map would be drawn. So where you have this tongue of warm air, if you will, and notice the higher height for the surface of constant pressure because the air is more vertically expanded. On a weather map, on an upper air chart, that would look like a bend in the height contour. These are the contour lines shown toward the north in the northern hemisphere. And it's called a ridge, an area of high height contour lines, high pressure on an upper air map. It's called a ridge, drawn with this kind of jagged line. Colder air aloft, okay, lower atmospheric pressure aloft, okay, you'd see a downward bend in the contour lines. Basically a U in the northern hemisphere, a dip, a southward dip in the contour lines, and that's called a trough, drawn by the dashed lines. It's an area of low pressure, okay? And upper air charts are plotted at different pressure levels, but some of the common levels where contour lines are plotted include the 850 millibar level, which has an average height of about a mile above sea level, but it varies, okay? Where it's higher, that means warmer air. Where it's lower, colder air. And this 850 millibar level is useful because it can be used to help detect winds, direction, and speed for the hills, the mountains, like around the Bay Area, right? Mount Hamilton, 4,000 plus feet. Mount Diablo, near 4,000 feet. 700 millibar chart has an average height of about 10,000 feet. This is a useful chart to look at for seeing areas of moisture and winds and how they're bringing in more moisture or warmer air or colder, drier air. 500 millibar chart has an average height of 18,000 feet. This is useful for seeing basically rising or sinking air. We'll talk about upper air charts more later, but it can be used to detect areas of rising or sinking air. We'll talk about how. And the 300 millibar level is the jet stream level. The jet stream is found around 30,000 feet. This is a very useful chart to look at because it turns out on the upper air charts, the winds blow parallel to the contour lines. So if you have a contour lines plotted for the 300 millibar level, okay, you can easily see the wind directions. You just follow the lines. And this is useful because, one, airplanes fly at cruising altitude of 30 to 35, maybe 38, 39,000 feet near the jet stream. And so it's useful to see how if you're going to have a strong tailwind or a strong headwind, as well as how strong. The closer to the contour lines, the stronger the winds. Also, the storms, the low pressure systems, the high pressure systems, the anticyclones follow the upper air winds. They're steered by them. So if you look at an upper air chart, a 300 millibar chart, you can determine which way the storms are going to move or which way the high pressure systems will move and how fast, okay? So very useful information can be provided by the upper air charts. Now, here are two different maps. One is a surface map, so it's basically supposed to be for sea level, showing sea level pressure. And we have an upper air map, the 500 millibar level map showing hot contour lines, whereas the surface map shows isobars. Okay, the black or dark gray solid lines are isobars with values separated by 4 millibars, intervals of 4 millibars for the isobars. Okay, 1,024 millibars here, high pressure. Okay, the center of this area of higher pressure, it's a high. Generally, as you may have seen on the news and on the Weather Channel, areas of high pressure at the surface are shown by blue H's. Areas of low pressure at the surface are shown by red L's. Okay? Notice that the pressure decreases as you go from this high centered over southern Illinois, right? Obama, right? Illinois. As you go west-northwest or northwest, your pressure is decreasing as you go over the plains into the Rockies, and by the time you get to western or southwestern Montana, right, northeastern Idaho, your pressure is below 1,008 millibars. You're low. Now the purple lines, arrows, are streamlines, indicating the direction from which the wind is blowing. They're used to basically give a meteorologist a sense of how the air is moving. Notice the winds blow counterclockwise and inward around the low. See that? That's what we said back in the day, right? Flashback Friday, because I'm recording this on Friday for Lecture 1. For high pressure at the surface, can you get a sense of how the winds are blowing? Clockwise and outward, and counterclockwise and inward to this low off the northeast U.S. Okay? And also across the isobars. We'll talk more about this, but they blow across the isobars because of friction. Okay, not parallel to the isobars. Areas of low pressure are called cyclones. Areas of high pressure are called anticyclones. Now, on this upper air map, we also have areas of high and low pressure, but it's a little different here. On an upper air map, to show high and low pressure, you could still draw H's and L's, but generally one color, such as purple or maybe black. Generally, the blue H's and red L's are reserved for the surface maps. And notice you also have these dark gray solid lines with numbers, but you're not looking at isobars, you're looking at heights in meters. 5400 meters. Think about that. If you're traveling on this 5400 meters line, what does that mean? What does that number mean? Well, look, upper air map, 500 millibars. That shows you the height. You'd have to go above sea level to reach the 500 millibar level. Okay? So if you're right along this 5400 meter line here in Spokane, Washington, right, or eastern Montana, that means you'd have to go 5400 meters okay, which is probably about 17,500 feet, roughly, something like that, feet to reach the 500 millibar level. But if you're here in Baja California, or along the U.S.-Mexico border here in extreme western Texas, you'd have to go 5,700 meters above the surface, and that's closer to 19,000 feet above the surface to reach. Why? Warmer air, right? So in warmer air, the molecules expand vertically with height, so you have to go higher up to drop to the same pressure level. Notice, as you go north, despite the waves, we'll talk about this, the ridges, the troughs, as you go farther north, what happens? Contour height decreases because the air generally becomes colder as you go poleward. As you go southward in the northern hemisphere, equatorward, air becomes warmer, height contours increase. Okay, now, see this U shape in the height contours, this southward bend or dip? That is a trough, an area of low pressure. Troughs are usually associated with colder air, and ahead of them, often storms. Okay, typically we'll talk about storms ride on the eastern side of troughs. Okay, ridges are these upside down U's, these northward tongues in the jet stream, are associated with warm air, usually clear air too, subsidence, sinking air. Okay. Here's another trough over New England. Also, the dashed red lines are isotherms, the temperatures in degrees Celsius at the 500 millibar level. Again, as you'd expect, you go farther north, the temperatures get colder. Farther south, the temperatures get warmer. Notice that the winds, again, we have these purple wind arrows, the streamline showing us wind motion direction. Notice they blow parallel to the contour lines. Okay? So aloft in higher elevations above the level of friction, right? Friction is significant near the ground where the air is basically feeling the ground. It's in contact with the ground, right? It's but above that, the air, there's no friction, and so the winds blow more parallel to the contours, height contour lines. Okay. And upper air maps are extremely important in forecasting weather because not only they can show the direction the surface highs and lows will move, but whether they weaken or intensify. You want to see, is the low going to become stronger at the surface with stronger winds? You actually have to look for, we'll talk about convergence and divergence aloft, which you can use the 500 millibar map for. Okay. Now, reiteration here is that for a ridge of high pressure, shown by an upper air map, the height contours bend strongly to the north in the northern hemisphere, south in the southern hemisphere, but we don't want to confuse you, right? And so you could say for both hemispheres poleward, okay? And strong ridges are accompanied by warm and dry weather at the surface. Heat waves in the Bay Area, you guys, heat waves occur when a strong ridge remains over an area for an extended period of time. Okay, so like if the Bay Area has a heat wave, usually has to last at least a few days, right? Say we have a few days where the temperatures in San Jose are near 100, 105 plus Fahrenheit. There's probably a strong ridge over us, over the West Coast. Okay. Whereas in troughs in the northern hemisphere, the contour lines bend strongly to the south. They look like U's. Strong troughs are typically preceded by stormy weather and colder air. What usually happens in the wintertime is that ahead of the trough, a low pressure system will come in. It will rain, and then it cools, and behind the cold front, the colder, drier air comes in, and the coldest air comes in. Okay, and the trough passes us. Okay, we're ahead of the trough, just ahead of the trough, the eastern side, or in the right-hand side of the trough, is where you see generally the precipitation before the colder air filters in. Okay. Okay, now that we've reviewed pressure and we understand how horizontal differences in pressure produce winds, and we understand how we show differences in pressure at the surface or aloft, and we understand the connection between temperature differences and pressure differences, now we are in a good position to talk about why the wind blows. And once it starts moving, the horizontal wind moves, what happens to it? What forces influence it?